When there's something that you are pretty sure has to be right, and there's something else which you're pretty sure has to be right, but they conflict with each other. They can't both be true. To me, that's where my mind is drawn. I think almost everything I ever did was a product of that. But yeah, that's where I am.
And it does take a certain kind of confidence, right?
Of course I've been wrong many, many times, but I never had a fear of it.
Yeah.
I always thought it's okay to be wrong. Even Einstein was wrong.
So I'm so pleased to be speaking with Leonard Susskind tonight. He's a native New Yorker, got his degrees at City College and at Cornell, and then has had a long, illustrious career at Stanford, where he's the Felix Bloch Professor of Physics. He has so many accolades that we'd be here all night, but the ones perhaps of most relevant to our discussion, he is one of the co-founders of string theory. He's had profound impact on our understanding of black holes, on our understanding of quantum mechanics, on our understanding of space and time and cosmology. So we'll try to get to some of those topics here tonight. So Lenny, thank you so much for joining us.
Thank you. When people come along and say, oh, I'm so terrific, I invented string theory, blah, 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 it really isn't very interesting to me. But when somebody like Brian, who knows what he's talking about, says it, it feels nice. Thank you, Brian.
No, thank you. So please let's give a warm welcome to Leonard Susskind. So Lenny, we're going to get into some of the science in just a moment, but I thought it might be nice to begin with just a little bit of your background. So you grew up, I guess, in the Bronx, and your initial profession was as a plumber.
Everybody knows that. That's just true. Plumbing at the time when I was engaged in plumbing, my father was a plumber. Okay, he came from a rather intellectual background. His father was something of an artist. I only learned fairly recently that my grandfather was probably one of the people who was responsible for the beauty of the hotel. What's the name of the hotel? The Waldorf Astoria. The Waldorf Hysteria? No, Astoria. Evidently, he was one of the artisans who designed and built the beautiful interiors.
Fantastic.
He was also a gambler, and a serious gambler. And so my father, because his father was a gambler and lost all the family money and was thrown out in the street and all those sorts of things, had to go to work as a plumber. Why a plumber? I never really understood why he went into plumbing, but that was what was available. At the age of 12, he had to leave school. And so for him, he always thought about it as two possible things that a young kid his age from the South Bronx, Jewish kid from the South Bronx, could do with himself under those circumstances. The first was to become a gangster, a criminal. That was something you could do. That was not my father's style. He was a good boy. And the other was to go to work in the building trades or anything like that. So while the family was rather educated, they spoke many languages. They were, he had to go to become a plumber. That's what he did. Now, when I got to be about 12 years old, I was out in the streets and doing stuff maybe I shouldn't have been doing, and this worried my father a great deal. He wasn't worried about that I had enough money to make and so forth, but he was worried that I was getting into trouble. And so from the age of about 12 or 13, he put me to work in his plumbing shop as a plumber. Of course, I wasn't a plumber at 12, but I was a plumber at 15 and 16. And, that was my career until I found something else. What was something else? I was good at math. In high school, I was good at math. I knew I was good at it, and so I got fascinated by it. Somehow that led to physics. And it wasn't until the age of 20 that I really knew that there was a subject of physics.
Was there a moment? I mean, when...
I remember a couple of moments. I remember walking home from high school. I was walking home, and I was on, I don't remember the date, but the newspaper was out, and the newspaper said, Einstein dies. I was 15 years old. What was that? That was 1955.
55, for sure. Yeah.
And I remember just being thunderstruck. I didn't know what Einstein had done, but I knew that it was something that I wanted to know about. And just there was some heroic idea of what he did, which was understanding nature. And at that point, I knew that was something I wanted to do. But I didn't know about physics. I knew about mathematics. And so it took a couple of years. I went to engineering school at CCNY.
Oh.
I went to engineering school. I was bad at that also. I didn't like it. I didn't want to do that. And the engineering professor, his name was Harold Rothbart. He became a longtime friend of mine afterwards. Okay, I'll tell you the story. We had to do mechanical drawings. You know what a mechanical drawing is. In those days, there weren't computers. You actually had to do it with a pen, India ink, and the pens were truly an invention of the devil. They were called ruling pens. I don't know, has anybody ever seen a ruling pen? Ah, Larry here has seen a ruling pen. Okay, ruling pen sort of looks like my arm, except much shorter. And there are two little nibs at the end like that. Am I getting it right? And you drop the India ink in there, and it's held in place by what's called capillary attraction. Okay. And then you rule with the ruling pen. Unless you have a very steady hand, you will leave a blob of ink. And if you leave a blob of ink, the drawing doesn't count. So after about 6 or 7 weeks of the class, Harold Rothbart came over to me and he said, "You are working on your first drawing, everybody else is working on their fifth drawing." He said, "I'm going to fail you in this course." I said, "Wait a minute, Professor Rothbart, no, you can't fail me. My wife, I was married at the time, my wife is waiting for me, my child is waiting for me, my father is waiting for me to go into business with him. You can't do that." I thought, this guy thinks I'm a real idiot. He stepped back and he looked at me and he said, "You're really, really smart. You should not be doing this kind of thing. You should be going into one of the sciences." And he simply helped me find the right science that I really wanted to get into. So Harold Rothbart was a major influence on my life. It got me out from certainly got me out from plumbing, got me out from engineering, and somehow made me aware of the world of physics. And that was at CCNY. CCNY was the right place for me. I could have gone, I was probably smart enough to go to Harvard, probably too smart to go to Harvard. Columbia, I could have gone to Columbia. CCNY was exactly the right place for me.
And so when you went to physics, though, I mean, there are many different styles of our theoretical colleagues. I mean,
style is the right word.
Yeah, because like, for instance, there are those who focus on just calculation, getting some result, like Tom Kinoshita at Cornell, just because you mentioned it. So this is a physicist who spent decades calculating the magnetic properties of electrons. He took me into his office once when I was a junior faculty member there. He showed me these notebooks filled with pages of calculation. So, but that's never really been your style. You're drawn to the big, I mean, maybe the Einstein motivation. You're drawn to the big question.
I don't want to diminish what Tom was interested in.
No, not at all.
Kinoshita was interested in. Tom was an extremely smart, deep thinker.
Yeah.
But he loved the process of doing calculation.
Yeah.
Calculation didn't mean adding up columns of numbers. Of course, that was part of it. It was calculating Feynman diagrams. And Feynman diagrams are a subtle business. They're not something that you just learn in high school and learn to do. He was a master of it.
Yeah.
But yes, his style was computational. My style was very different. I think what draws me, the thing that draws me in physics, is conflict of principles. When there's something that you are pretty sure has to be right, and there's something else which you're pretty sure has to be right, but they conflict with each other. They can't both be true. To me, that's where my mind is drawn.
Yeah, I think it's a perfect summary. I was just, in preparation for tonight, just thinking about all the major contributions, and they do fit into that paradigm, almost all of them. And I'd like to get to a few of those in just one moment. But one other question before we do. So, there's mathematics, as you described, which is the key language of theoretical physics. There's also this mysterious thing called intuition or inspiration.
Who knows what it is, yes.
So do you find yourself being driven more by the mathematics or by an inner intuition that interfaces with it in
Yeah,
some
no,
way?
it's the latter. It's very much the latter. It's interesting. I have a very good friend. He's also a good friend of yours. His name is Edward Witten. He's one of the world's great mathematicians. He's also one of the world's great physicists. Most people would think that we have almost diametrically opposite propensities. It's not true. We get together and we really enjoy talking to each other. We talk the same language. So, yeah, I'm not a natural mathematician. He is. But intuition, and what intuition is, it's hard to say. It's a combination of experience, intuitive thinking. It's hard to say what it is. But yeah, that's where I am.
And it does take a certain kind of confidence, right?
Yeah.
To follow your intuition.
Yeah. A willingness to be wrong, incidentally.
I mean, have you found yourself wrong in ways that were uncomfortable?
Oh,
were
no,
they
I have never
generally-
been wrong.
Generally
No,
just
I've
learning?
never been wrong.
Yeah.
Laugh. Of course I've been wrong many, many times, but I never had a fear of it.
Yeah.
I always thought it's okay to be wrong. Even Einstein was wrong.
Many times.
Many times.
Yeah, for sure.
It's okay.
And so getting to the conflict of principles, there have been a number of places where you've played a key role in trying to ease the hostility between principles. And I wanted
hostility
to start with,
between, I thought you were going to say between people.
No, between the principles. Although there are people, of course, involved, because many times there's a person who's driving a certain principle. And so black holes are an interesting example. And I thought we would just quickly give a little bit of background on them and then get to the clash. So Einstein writes down general relativity in about 1915. Shortly thereafter, Schwarzschild writes down the first exact solution of Einstein's math. And within there is this notion of a black hole. And Einstein resists.
He didn't like it.
Didn't like this idea.
You know, before we talk about that, let me say something about the field itself and the whole business.
Yeah.
It's a very human business. People don't agree. They disagree, they fight, they sometimes even on the nasty side, not usually. And it's a very human business. The conflict of principle can sometimes turn out to be a conflict between people. It's like anything else in the world. Physicists are not immune from the human passions, shall we say. So get the idea that physics is simple because it's either right or wrong. That may be true in the end of the day. In the end of the day, there's a little kernel of truth which doesn't go away. Newton's laws are not going to go away, but at the time when these things are being created, it's like anything else, any other human endeavor. There are all sorts of conflicts, there are all sorts of passions, there are angers, there's the opposite of angers. And so one of the examples of this was my relationship with Stephen Hawking. Yes. So you were about to bring
As
that
we were
up.
headed, yeah, exactly.
Right. I just wanted to say that there is this human element to things that is not just, it's either right or wrong.
Right.
At least not in the beginning.
And so that conflict was around black holes.
Yes,
with two
certainly.
different views. And just to get there, so Einstein resists this idea, doesn't think that black holes could be real. I think he wrote papers into the 1940s trying to prove mathematically that black holes could not actually be out there.
He did.
And you began to think about black holes, of course, well before like the Event Horizon Telescope actually showed us that we're there.
Way before that. But
well before even Andrea Ghez showing the stars in orbit around the black hole in the center of our galaxy. Did the absence of an actual black hole ever dissuade you?
Not at all.
And why is that?
Well, first of all, don't leave Stephen out of the story.
Yes, of course.
I mean, of course. And all right, so it was pretty obvious to me. Most physicists accepted general relativity as a theory of gravity. There was not much question about that. There was a question about whether it's worth working on.
Yes.
When we were young, I was young before you were young, but when we were young, it was frowned on to some extent to work on general relativity. It was considered a little bit flaky, but not because it was wrong or anything like that. It was too remote, too far out of the mainstream. So Stephen, of course, wasn't dissuaded by that. And he and a gentleman named Bekenstein had understood a great many very, very interesting things about black holes. So I wasn't the person who came in and in any sense discovered black holes in any sense. I could not understand why Einstein himself was so negative about it. General relativity was obviously a good and an important theory of gravity. It was the right theory of gravity. I knew it, my friends knew it, and so forth. And the black hole was a solution of his equations. There was no doubting that. The question at the time was, okay, it's a solution of the equations. There are lots of solutions of the equations. Why should we be so focused on this one? What was special about the black hole that made for giving up everything else, let's say, and focusing on it?
Right.
All right, it was Stephen again. Stephen had pointed out something which he thought was true about black holes, that anything that falls into a black hole is lost. It's gone. It cannot come back out. And when you say anything, the right word is information, distinctions between things. So what's the idea? What is information? Information is simply the distinction between things. You have a piece of information when you know that something is A and not B. So if you can distinguish between two things and you know one of them and not the other one, that's a piece of information. All right, so a black hole is something that you can throw a piece of information into. By that meaning you can throw a book in, you can throw whatever you like. And it was a very, very central principle of physics that nothing ever really gets lost. When anything appears to get lost, why would it get lost? It gets too jumbled up. It gets too diluted with too many degrees of freedom and so forth. That's illusory. The real information is still stored there in some way or another. For example, in just the gas of evaporating products and so forth. Stephen didn't believe that. Stephen thought that black holes were very special this way, that they would be, in fact, I mean, he pretty much, I would have to say that he pretty much thought that his legacy in physics would be that information is not conserved.
Yeah.
There were two of us who reacted to that very negatively, Gerard de Tuft and myself. And just instinct and our understanding of previous physics and how previous physics worked just said, that can't be right. Can I explain why I was so sure that it can't be right? No. No, it's hard. I mean, it's one of these intuitive things.
And again, the clash of principles.
That was a big clash. That was certainly a clash of principles. The principles were that the equations of general relativity seemed to allow things to fall into the horizon of a black hole. And the principles of general relativity would say that nothing can cross back out. That was general relativity, Einstein's great theory. The principles of quantum mechanics says nothing is ever lost in that sense. It's called unitarity, but don't worry, every time I hear unitarity, I think about the unitary executive principle, which we don't want to go hear about, do we?
Probably not in this
Probably
setting,
not.
but
Right.
Yes.
Right, but it's got nothing to do with that.
Yeah.
It says nothing other than information is never lost. That's the principle. I grew up not as a general relativist, I grew up as a quantum theorist. And so unitarity to me was one of those things which you don't play around with. It's central, like the second law of thermodynamics. And here was Stephen saying it was wrong, that things do get lost. I just rejected it. I just thought it had to be wrong. There was some instinct, some intuitive instinct. Gerard de Tuft had the same intuitive instinct. He was also a major influence in quantum mechanics at the time. And just couldn't accept it. So we thought about it, made arguments about it, found one argument after another, all of which said that Stephen was wrong. Stephen stuck to his guns. He wouldn't budge. It was a difficult time for both him and me and all of us. We liked each other. We were very fond of each other, and yet we were bang.
Yeah. And so how did this play out then from that
Well,
point forward?
Okay. It played out. Part of it was this thing called the holographic principle.
Yes.
Okay. Black holes have horizons. They're like a thin, infinitely thin shell surrounding, but they're not real shells. They're just mathematical surfaces. Anything that goes past the horizon, in principle, is stuck behind the horizon. What Stephen accepted that as a law of nature, that anything that goes through the horizon is gone. One of the first things that struck me, it's weird because you might say this really has nothing to do with black holes. Well, it doesn't. You know what a hologram is? Everybody know what a hologram is? A hologram is a piece of film, two-dimensional, which encodes a complete three-dimensional reality in it. You can decode, the hologram is just a two-dimensional piece of film. It's not three-dimensional. But if you have a hologram, you can do whatever it takes. It involves shining light on it and other things to reconstruct a complete three-dimensional reality. That's called a hologram. It struck me at the time that the horizon of a black hole was similar to a hologram. All of the information that falls onto the black hole appears to fall toward the horizon and get stuck there and never go through it, like the holographic film. On the other hand, anything that goes into the black hole, just as like any ordinary thing, it just falls into the black hole and with nothing terrible happening to it. It struck me that this was very similar to what happens in a hologram, that the hologram is a two-dimensional image which encodes fully three-dimensional reality, and at the same time has much less information in it than you might have thought was in the interior of the hologram. The hologram is a two-dimensional surface. It has an interior. So I had been thinking about that a little bit, but I hadn't really said it in my own head that way. Judy, don't get upset by this. This was a long, long time ago, long before I knew you. My friend and I, Laris, were walking through Stanford, where there is a little museum of science in the physics department. And one of the museum illustrations was a hologram. And the hologram was a hologram of a very pretty young lady. She was extremely pretty. And I remember the two of us stopped and looked at it, and we said to each other, isn't it too bad that she's not really three-dimensional? And I remember the incident very clearly, and I said to Laris, Thalasius, my friend, that's got to be the way black holes work. The horizon has to be like a hologram of some reality. Not necessarily a pretty girl, but whatever falls in. That seemed crazy, of course. What was it that Sherlock Holmes said? When you've tried everything and nothing works, the last thing, there's a quote of his.
No doubt, yes.
Yeah, what it says is, after you've tried everything and nothing works, and you have one last thing, no matter how crazy it is, it's got to be the right answer because there is nothing else. Go look it up, Sherlock Holmes. He was a very wise man, incidentally.
Now, this is a wild idea, right?
Yeah,
so you're saying that if we throw an encyclopedia into a black hole,
right,
the encyclopedia can go in, but its information kind of sticks to the surface,
right,
and is available,
right,
to the external world, so the information is still there.
Not easily.
Not
yes.
easily,
Okay.
right.
So yes. So at the time, look, I was a pretty well-known physicist. I was not the only one who had this thought. Gerard Hooft was the other one. Everybody know the name of Hooft? Hooft is one of the great physicists of the 20th century. He really is. A Dutchman. He's somehow not as famous as he should be. But Gerard had exactly the same idea about the same time. We talked about it a little bit and so forth, but the point was that Gerard was a very famous physicist. I was pretty well known. I think most of our colleagues thought that we had gone berserk. lost on marbles. I do remember somebody, I know who it was even, but saying to me, you two guys used to be very good physicists. You
Really?
lost your marbles.
Someone actually,
Yeah.
well.
Yeah, right.
Did that give you pause at all, or you're like, no, I'm going to stick?
No, I knew it was right. By that time, I knew it was right. No,
Right.
no, I never had that. I never had those insecurities. Neither, by the way, does the Tuft. He's a man of great security. There was only one person who really supported the idea thoroughly. It was Edward.
Is that right?
Yeah, he was very enchanted with the idea, thought it was right. But it didn't get any real traction for a couple of years. How many years? Maybe 3-4 years, until a physicist by the name of Juan Maldacena. How many people have heard of Juan Maldacena? He is also one of the very great physicists of my. He's younger than me. He's even younger than
Yes,
you.
he is.
But he, somewhat independently, I think, put together a description of a particular kind of space-time, anti-de Sitter space. Don't worry about what it is. And it was a description, a quantum mechanical description, in which all of the activity, the encoding of information, was on the surface. In other words, it really was an instance, a mathematically precise instance of the holographic principle in action. It was too mathematically precise to ignore it. And that was very much the watershed. Yeah.
And so if we take that principle, now initially it was in the context of black holes, that the surface
Initially in
of
the
the
context
hologram,
of black holes.
and then in the context that Juan Maldacena, it was a little bit different. You've extracted to a general principle where any region of space should be described, the physics within it should be described by physics taking place on a surrounding boundary. Like in this room, all of us here would be the inside, and the physics would be taking place on the ceiling and the walls and the floor, and yet that physics would describe everything that's happening in here.
Yeah, the logic, there was a very simple logic to it. Very simple logic on something like this. Imagine a region of space, let it be spherical. And there's all kinds of things going on in it. And there is a measure of the amount of information. It's called the entropy in the region. Entropy is another word for information.
Or hidden information.
Hidden information. Why is it hidden? Because it's encoded in too many degrees of freedom to keep track of, whatever. Entropy is information. So we have this round region. It has a bunch of stuff in it. And ordinarily, people would have quantified the amount of information in there by saying it was proportional to the volume. Why not? I mean, each little piece of volume can contain some information, and you might think the numerical value of the information would be proportional to the volume. On the other hand, what I argued was that you could imagine taking a bunch of matter, a shell of matter, contracting it, and trapping all that matter inside the horizon of a black hole. And it had already been established by Hawking and by Bekenstein that the entropy of a black hole is equal to the area of the horizon, not the volume. So what that said was that the maximum amount of information you can ever have in that region, that you can ever hide in that region, is proportional to the amount that you can hide in a black hole, and that was known by then to be proportional to the area. Area, that's like a surface. So that was my argument for it.
Yeah.
Tufts was a little bit different. But Maldacena came along with an extremely precise, mathematically very beautiful illustration of it, and that was something that couldn't be ignored. So by that point, I think the community made a switch.
Yeah, so I think it is now widely accepted. One question, and I don't want to get bogged down too much in the details, but Juan Maldacena's version of this principle isn't exactly our universe, right? It has,
it's exactly not our universe.
Right, but you feel confident that even though we haven't yet, say, formulated a generalization of what Juan did for our universe, that it still applies?
Well, I think the point is that all of the arguments that were made to say that information is lost, all of them would have applied to this example. So while it is not the world we live in, the arguments that would support Stephen Hawking were applicable. And so it was clear that if Juan was right, in this particular context, Stephen had to be wrong. It was not a matter of anti-de Sitter space is the word you're looking for. I know you're not looking for it, you know it, but anti-de Sitter space was the kind of space you're talking about. And it was not a matter of whether our world, it's a matter of whether it was a consistent world, whether it was mathematically consistent. And if it is mathematically consistent, how does it avoid this dilemma, this conflict of principle, which says that both things can't be true?
Right.
So it really had very little to do with the question of whether our particular universe that evolved out of particular cosmological things was the right thing. It was whether it's a possible thing, and if it is a possible thing, how does it avoid the...
Right. Now, ultimately, Stephen, who was adamant for decades, he did come around to this. That maybe I'm not giving the right summary. Would you say that he didn't really, or
He did and he didn't. He didn't want to let go. He didn't want to let go. And in some sense, I think he was right to push things to the. Well, first of all, I admired Stephen enormously. I certainly don't want to say anything negative about his views, certainly not. I would say he pushed to the limits a view that ultimately collapsed. I think in the end, certainly by the end, he knew that he was wrong.
Yeah.
But he held out for a long time.
Sure. Now, the work of Maldacena was in the context of string theory, although it's a more general idea, but it used the ingredients of string
theory. It used the ingredients of string theory to make a very precise mathematical argument.
Right.
But the thing itself was much more general than string theory.
So can we just take a step back, though, on the string theory front? Because it's another clash of principles that you played a vital role in giving us insight into. So just very quickly on the history, back in the 60s, people were working with particle physics experiments at colliders, trying to understand what happens when particles slam into each other. And a gentleman named Gabriele Veneziano writes down an inspirational formula, kind of pulled it out of thin air, that seems to describe the data, but he doesn't really know what the formula is. You look at that formula and you realize that there's a string inside of this thing.
Right. Let's go back to conflict of principle for a minute.
Please,
what was the conflict of principle there? There was a widespread belief in the particle physics community at that time that you could not see into the interior, the guts of what goes on inside particles. Yep. They were too small in principle that it was absolutely impossible, and that physics should not be concerned with the details of the internal structure of particles. That was called S-matrix theory, and it was very prevalent in Berkeley. And I was a postdoc in Berkeley, so I had no choice except I didn't have to accept it, but I did have to think about it. Didn't seem right to me that you can't, particles aren't that small after all. A proton is a rather fat thing. It didn't seem right to me that that view was right. And I made an argument about it. The argument went this way. If you have a proton and it's moving down to your right with a very high velocity, close to the speed of light, all the internal motions slow down. They may be moving fast, but the internal motions slow down.
Special relativity.
Special relativity, nothing but special relativity. And that means that as it's moving along, if you imagined moving along, it's not moving with quite the speed of light. So you move along with it, and you take a series of photographs of it, you see it slowed down, and you can see the internal processes taking place. This was a consequence of special relativity. I thought it had to be wrong. And so when Veneziano put his formula out, I took a look at it and I said, how can we understand from his formula, if we imagine that the proton was moving very fast, how can we understand what's going on in its internal structure. There were things about his formula which suggested, everybody know what the harmonic oscillator is? Harmonic oscillator is a vibrating system. There were things
like a pendulum.
Pendulum or a spring, and there were things in the formula which are extremely suggestive of the harmonic oscillator, which is that's the world's simplest quantum mechanical system. So I took a look at it and I tried playing around with what I knew about harmonic oscillators, trying to see if I could reproduce his formula in some funny way by thinking of the proton as a bunch of vibrating things. And after some not quite successes, I was successful. It wasn't a simple spring with a particle on it. It was a chain of springs, a string, what's called a string now. So I got very excited. By the way, I thought I was the only one in the world who knew that. I wasn't. There was a very famous physicist at the time who did essentially the same thing, Nambu. Yoichiro Nambu, a Japanese-American physicist, he was Japanese. And I found out after a couple of weeks, those days things moved slower. You wrote a paper, it could take 6 weeks to write the paper, but by the time the secretary had properly gotten all the equations together, it could be 3 weeks, another 3 weeks so it took a long time to get the paper out. And after about 6 or 7 weeks or whatever it was, I found out that Nambu had done the same thing. Okay. Did I have mixed feelings? I had very mixed feelings. On the one hand, I was terribly disappointed that I was not the only one who knew it. On the other hand, Nambu had always been a great hero of mine. He was one of the greats, and to myself, well, if I can do what Nambu did, it's okay. It's okay. It's pretty good.
Yeah.
Right.
And so you had this idea of a spring or a string sort of being the internal structure. In the end, the idea didn't work in that context as well as perhaps you would have hoped, right? I mean, we had to push it in order to think about this in the gravitational context.
Well, yes, okay, so, right. This kind of string idea is rather universal in many ways.
Yeah.
It can, just like many things could be point particles, many things can be strings. The idea that a proton or a neutron or a meson, which are almost visible, you can almost see them, they're so big. How big? 10 to the minus 13 centimeters. That they are strings, that idea I think is correct.
Yeah.
I think that idea is essentially completely correct. But there was a problem with it, as you said. One of the problems with it is it had a kind of particle in its spectrum. In other words, it was a particle that it was describing which nobody knew how to get rid of. It is not a particle that is there in hadron. Hadron physics means protons, neutrons, mesons. It had no place in that structure. In fact, the particle was in every respect similar to a graviton. But we weren't trying to describe gravity. We were trying to describe protons and neutrons.
Where graviton would be the smallest particle carrying the gravitational force.
Right. And if this theory had anything to do with gravitation, it would have to take place on a scale which was 19 orders of magnitude smaller than a proton. This was not my discovery. This was the discovery of John Schwartz and what was his, the French physicist. Joel Shirk.
We did it together.
Yeah, they did it together. They realized that the same mathematics that we had been using to try to describe protons and neutrons, the same mathematics, the same string ideas, could apply on 19 orders of magnitude smaller distance scale, could apply to the graviton, to very, very fundamental gravitational interactions and so forth. That was really the start of the connection between gravity and string theory.
And so that was sort of a remarkable moment because, talking of clashes of principles again, people had long known that general relativity describing gravity, which is relevant for big stuff, quantum mechanics, relevant for things are small, each worked in their own realm.
Right.
But any time you kind of tried to put gravity and quantum mechanics together in the traditional way, it didn't work.
Right.
And yet here, gravity is sort of dropping out.
Dropping out, yeah. Yeah, I think that the history of the last 20, 25 years has been something like this. There are systems that we study in physics. The harmonic oscillator is one of them. The hydrogen atom is another one. And these things usually start with some classical system. The classical system for a hydrogen atom is a perfectly ordinary classical nucleus with an electron going around it, subject to the same rules that govern the solar system, Newton's equations of motion and so forth. And then you do a process to the classical theory called quantization. It's a mathematical procedure where you make certain substitutions in the equations, and all of a sudden you have a quantized version of it, and that's called the quantized harmonic oscillator or the quantized hydrogen atom. Okay, that was the rule. That's the rules that Dirac laid down.
And that we teach the students.
Right, and how to take a classical system and convert it to a quantum system. It's called quantization. So for a long time, people tried to take general relativity, Dirac himself did, and tried to take general relativity as a classical system and subject to it the rules of quantization to find quantum gravity. Never worked.
Yeah.
That was the disaster. That never worked. It was always disastrous, always led to contradictions, led to mathematical contradictions, infinities all over the place, and terrible stuff. I think what we've discovered over the last 20, 25 years is that it's a mistake, and it's a mistake because gravity and quantum mechanics are too closely connected to pull them apart and then subject them to quantization and put them together again. And many, many things make you feel that they're almost the same thing in many ways. And I think we'll have much more success in not quantizing gravity, but just trying to think of them as more or less the same thing. And that's where we are now.
In fact, one of the remarkable moments in the history of the subject of string theory is when you study the mathematics of a vibrating string and you're a good enough mathematician, you can find Einstein's equations that he spent 10 years laboring to
Isn't it incredible?
Put forward. They come right out of the theory.
They pop right into your hands.
Yeah.
Yeah. Right. So the mistake that we made was not thinking that gravity and quantum mechanics were sufficiently separated that it needed a process to bring them together. In fact, they're almost the same thing. And that may not strike you as obvious. Of course it's not. Gravity, as you said, is about big things. Quantum mechanics is about small things. And it was the black hole that brought them together. The black hole was both big and heavy and also extremely quantum mechanical.
Yeah.
So that's where all of that took place.
And so by the mid-1980s, when I started in graduate school...
Are you that young?
Yeah, well, I guess. I don't look at it anymore. But, so we had this idea that finally gravity and quantum mechanics were no longer antagonists. They were playing well together. And it was so exciting. People spoke of the end of physics. This is going to be the final theory. We're now many years from that.
Yes,
and
we are.
The critics, of course, emphasize that the theory is yet to make a specific testable prediction that's been confirmed by experiment.
And of course they're right. I mean,
that's right.
That's a correct statement.
And so I have my response to that. What do you say? You already began by saying, yes, they are right. But what do you answer to why should we still do it if physics is about making predictions that we can test?
Well, physics sometimes is about making predictions about things we can test. Other times it's about making internal consistency between different aspects of physics. One of the chief critics is a colleague of yours, I believe. And he is rather forcefully maintaining that string theory, until it can produce a success of the kind where you actually can produce a number, and that number can be checked with experiment, that it doesn't have any value. Well, I don't think that's true. I think the value here is, up till now, what it's done up till now is it's made clear that quantum mechanics and gravity can fit together, that they can fit together, and and not only fit together, but fit together extremely comfortably. It has not yet produced, and maybe it never will, it has not yet produced a detailed description of elementary particles, hasn't produced a detailed description of the electron and so forth. Maybe it never will, I don't know. But what are we supposed to do? Throw it away, saying it's worthless because it has not yet produced what we all had hoped in the beginning it would produce? No, you have to see it through.
Well, one of the enticing and alluring qualities is that it can get pretty close to describing the electrons and the quarks.
In some sense, yes.
You know,
in some sense, yes.
And so, where do you place the burden for why we haven't been able to take that step? Is it the extra dimensions where do you place the issue?
Well, okay. So I always talk about two versions of string theory, which I probably where's we thinking about going. One of them is a highly mathematically precise version. It relies on something called supersymmetry. Now, supersymmetry is a mathematical property that strings don't have to have, but specific versions of it have this particular symmetry. And that symmetry, whatever symmetry means, makes it easy to calculate with, makes it stable, gives it some very, very good properties.
And you can trust the results.
And you can trust the results mathematically. Mathematically. On the other hand, the world of observation is not supersymmetric. It would require that every particle, like an electron, has a counterpart of a different type which is not seen. So the world is not supersymmetric. Okay. The precise version of string theory, the one that mathematicians love, the one that mathematicians win Fields medals for. I never won a Fields medal, but they do. And that version of it is always supersymmetric. Supersymmetry is what makes it go, but the world is not. So I call that highly precise version string theory with a capital S. Very precise. You've worked on it. You've made a major contribution to it. But the real world is less precisely understood, and we don't know what's wrong with the precise version of it, except to say that there must be something bigger than the standard string theory picture, some a little more general, containing some elements that this very precise version doesn't contain. We don't know what they are. Could that be wrong? Sure, it could be wrong, but I get accused of using a phrase. It's the only game in town. It's the only mathematical game in town which seems to have properties which, as you said, look sort of like the real world.
Right.
It has particles similar to electrons. It has particles like photons. It has gauge symmetries, which means it has properties that the strong interactions, protons, neutrons, mesons have. So there's a whole bunch of properties that it has, which look temptingly like the real world. On the other hand, it's always reliant on this very, very special mathematical property, the supersymmetry, which the world doesn't have.
Now, there was a time, and there are some who would say we're still in that time, when the thought was maybe the world's almost supersymmetric. That is, the partner of the electron that you made reference to, the so-called selectron, and the partners of the quarks, the squarks, these other shadow particles.
Right.
We thought that they existed, but they were heavier than their counterparts.
Well, that, of course, would say it's not supersymmetric.
That's correct.
Right, but you could say almost supersymmetric.
Almost supersymmetric. And so that was certainly one of the motivations, not the only one, for building, say, the Large Hadron Collider, billions of dollars. We discovered the Higgs particle there. We're not going to talk about that in detail, so it's already had great successes. But we've not found those potential supersymmetric partners. Has that changed your thinking or disappointed you? Or
not as much as you might think. First of all, I was never one to think that this low energy supersymmetry was necessarily a consequence of. I didn't think that, but I didn't think not it either. I just didn't have any strong opinion about it. But I don't think the game is over. I think it's possible that the next round of experiments might discover it. I don't think it's. I don't think the game is ended.
Yeah, that's what I meant. We may be in that time right now.
I don't think the game is over.
But again, that wouldn't increase your confidence.
It would increase my confidence, but I don't think not finding them would be totally destructive to it either.
Yeah. Is there anything that you could imagine happening in the field that would convince you that this is time to put it away?
I'm 86 years old. I can think of something that would happen that would make me put it away. Well, certainly finding that it was mathematically inconsistent.
Yes.
But
that's the only thing that I can ever really come up with myself.
Right. I don't know the answer to that.
Or a dramatically better theory that made this not the only game.
A dramatic, right,
now, we should say there are other approaches.
There are, but I think both you and I probably don't put a lot of stock in them.
Right.
Right, that's the way the situation is now. It's a work in progress. Maybe it's not a work in progress. Maybe it's a work in the wrong direction. I don't just see what else we can do except to follow it through. Now, you have to understand, you say, why is physics like this now? Why wasn't it like this 100 years ago? The basic answer is experiments were a lot easier 100 years ago. They were tabletop experiments. You could do an electromagnetic experiment, Faraday, on his tabletop. You could, with a couple of magnets and maybe a dry cell. You do the experiments, and an experiment took days, maybe weeks, and not much more. As technology has become more and more remote and difficult and so forth, it started taking a year to do an experiment. Then it started taking 5 years to do an experiment. At some point, when big accelerators were necessary, it became a whole scientific lifetime to put together an accelerator and do it. And most accelerators, incidentally, were built for a single experiment. They're really just built for one experiment. And they just got harder and harder to the point now where to do the kind of experiment that we would like to see in order to confirm a little better supersymmetry and so forth would probably take 50 years. Something like that.
Right.
You may know better than me, but
it's hard to predict.
Something of order 50 years. Not just the experiment, but you got to build the accelerator.
And you got to raise the money.
There's all sorts of political obstructions. So it's not that physics has necessarily changed all that much. It's that the technology has become so fantastical that it takes a whole scientific lifetime or more to do an experiment. It's like building cathedrals. How long did it take to build a Notre Dame? 500, no, not 500, 200 years? And
they rebuilt it really quickly.
I know,
though,
right.
After the fire.
But,
yeah.
And people were willing to do it. People were willing to spend their lives on some small part of the cathedral. High-energy experimental physicists are doing something similar. They're spending some small amount of time putting together the pieces that have to go into not just the accelerator, but the detectors and all that sort of stuff. They're heroes, but it's going to take a long, long time before they answer any of our questions. And then the chances are that the questions that they will answer will only be the tip of the iceberg, and we'll just tell them, oh, well, okay, you got that one, but now let's go on to the next one. How long will it take you to build the next accelerator? Oh, 150 years. Maybe 1,000 years. You'll have to put it in space, and to build it. I once made a little calculation. It was not very smart. It was just straightforward. Just take the parameters that go into building an ordinary accelerator, and try to escalate it up to where the accelerator could produce Planck energy particles. Planck energy is the goal. That's the standard. We want to see things at that scale. Well, the answer is the accelerator would have to be essentially as big as the galaxy, maybe a little smaller, but that's the trouble that we're in now. So it's not that physicists are incompetent, the experimenters or the theorists or anything like that. It's just gotten hard.
So one final question before we wrap up. One of the other distinguishing qualities of string theory is that it does require more than the 3 dimensions of common experience. And so a big question early on was, where are those other dimensions? And one of the answers, not the only answer, is that they're curled up to a very small size. And when I began graduate school, the mathematics restricted the allowed ways that you could curl up the dimensions to 5 possibilities. And we're like, wow, let's just examine them all. Maybe we'll get some interesting experimental prediction. Over the years, the number of ways that you can curl them up has exploded. Mathematicians and creative physicists have found new ways to curl them up.
Including you?
I've done my share a little bit of that too.
Yeah.
So the number now, we often bandy about a number. It's somewhat meaningless, but 10 to the 500 is a number.
That's a number that's thrown around all the time.
A lot.
Yeah.
That's an enormous number of different ways that the extra dimensions could be curled up. You had a very creative idea, which was maybe we don't need to find just one to describe our universe. Maybe in some sense, all of these ways of curling up the dimensions might be real, in the sense that there might be many universes.
Many types of universes.
Many types of universes, and we're in the one where the curled up dimensions allow for physics that allows our bodies and chemistry and biology to exist, to actually take place. But the grander reality in this picture might have all of these other types of universes.
Yeah. That's
is that a mathematical idea to you, or do you
Yes,
really
it is a
envision
mathematical idea.
But, or do you take it in fully for what that would mean?
Well, it's hard to take in anything that grand fully, and the numbers are too big.
Do you ever picture one of the implications would be, like, there's many Lenny Susskinds out there in this grander scheme of reality. Do you ever, late at night, think about those other versions of you that would emerge in this way of thinking about things?
No, I usually fall asleep before I get started.
And so
I sleep well, incidentally. I'm a good sleeper.
And so, in the end of the day, this remarkable journey that you've had in
remarkable.
physics, has it shaped more than just your sense of how the world is put together? Has it kind of, in an emotional way, infused you with a sense of connection that you wouldn't have otherwise?
I suppose so, but at some level, I'm just having fun. I love the questions, try to find the answers. It's fun. It's fun to think about these things. And every so often, you get an idea that sticks. By sticks, I mean it becomes part of the subject. Incidentally, ideas like the holographic principle they tend to have a history which goes from wild, crazy idea to somewhat more sensible explanation of things. And ultimately, at the end of the chain, it becomes a tool of calculation, a tool of even a technological tool. People are using things like the holographic principle now to analyze the kind of quantum circuits that might go into a quantum computer. So it has become something of a tool. Ideas tend to drift in that direction, from the wildest crazy things eventually to tools.
Yeah.
And that is, I think, what's going on now.
Well, I have to say, on behalf of myself and the rest of the field, the fact that you have had so much fun has made our lives that much more fun.
Oh, I'm
because
glad
of
to
all
hear
the
it.
rich ideas that you have
Well,
provided.
thank
So
you for
thanks so
saying
much
so.
for joining us this evening.
Thank you for having me. You have to understand, Brian and I do this from time to time, and I get interviewed by a lot of people, but I'm not sure I prefer to get interviewed by anybody better than Brian.
Well, thank you.
It's great.
And on that note, we'll wrap it up. So thank you.
Thank you, Brian.